Hi, everybody. Thank you for joining. Sorry for the technical difficulties with the Zoom link. Hopefully the new link that we sent out worked for some of you. But before we get started here, I just want to give a little bit of an introduction on what the GSA is and our Limnoseries lectures. Today, we're going to be hearing a talk from Dr. Hamid Norouzi titled Opportunities and Challenges of Using Satellite Remote Sensing Observations for Monitoring Lakes and Inland Water Bodies. So thank you, Dr. Norouzi, for coming today. First, sorry, what was that?
My pleasure.
Thank you. So the Glion Student Association, we are a group of graduate students in Glion that organize network activities and workshops like these Limnoseries, where we have people come and give talks. And so the leadership team on this GSA is the chair, Rosie, the co-chair, Jenna, myself, and the co-chair-elect, Sophia LaFuente, as well as our GSA advisor, Catherine O'Reilly. So if some of you come to the Glion meeting this year, you'll see some of us there. And the workshop committee is part of the GSA, and we're the ones who put on these Limnoseries. And so these are the members of the GSA that are part of the workshop committee. And we also have two other subcommittees as part of the GSA, the communications subcommittee and the poster subcommittee. The communications committee helps manages the Glion blog. We host GSA seminars, and we coordinate communications on the Slack channel. And the poster committee helps to organize the poster sessions at our in-person all hands meetings. And so this year, after Dr. Nourouzi's talk, we will have one more talk on data visualization coming up in October. And also, for some reason, not on this list, we have an additional talk coming up in December that was just scheduled on ecological forecasting. So we have a few more talks to look forward to this year. And with that, I will stop sharing. And Dr. Nourouzi, if you want to share your screen.
Sure.
And just give you a quick introduction. Dr. Hamid Norouzi is a professor in the Department of Civil Engineering and Technology at New York City College of Technology, which is part of the CUNY system. And he's a joint appointment in the Department of Earth and Environmental Sciences as a doctoral faculty of the CUNY Graduate Center. Hamid is the co-director of Center for Remote Sensing of Earth System Sciences, and his research interests include GIS, remote sensing, and ground measurements in hydrology, climate, and earth system sciences. His research group has been focusing on applications of remote sensing in urban climate and lakes in the past few years. He's received funding to support his research from various federal and local agencies, and he has published his findings in this field. So thank you, and you can, with that, you can get started.
All right, thank you so much, Jenna. Appreciate it, and thanks everyone for attending this talk. Just want to start. My background is in remote sensing, and I'm a civil engineer by training. So I got distracted more and more from engineering and get into the field of remote sensing. And one of the topics that we are focusing on is about lakes. So I just want to start this talk with, this is the figure usually I show with the importance of water in a global scale, that we know that more than 97.5% of water that we have in our planet are salt water that are in the ocean. And from the 2.5% fresh water that we have, if we break it down, break it into its own 100%, about 69% are in glaciers and permanent snow covers that we don't immediately have access to. About 30% we have groundwater, soil moisture, permafrost, and about 0.3% of 2.5% we have in lakes and rivers that are mainly used for human purposes. We directly actually use them. And that's for the condition that if we can really have access to it, the water quality and everything that we want is in good shape, that will be basically 0.0076% of the total water, or H2O, that we have in our planet. So the projections of the Earth population. By a relatively recent study shows that the different models show about the lowest one between 9 to 12 billion people in our planet. That's going to happen basically in 2100. And that's the time that start to get, to a plateau scenario, or start basically coming down, depending on which scenario we go. However, we know that the Earth population and the resources and the water resources are not equally distributed everywhere. So, this is a map that shows the water stress in the region, in the Middle East and North Africa. For instance, we do have issues with the water availability. Even with the U.S. that we relatively show it as a light blue, not everywhere is the same. So depending on where you are in the U.S., as you know, they may change. So these are a lot of actually concerns that that makes us actually to use every tool and information that we have to manage and control and have a better understanding of water availability and the quality actually in our planet. So in the recent years, actually recent decades, I would say a couple of decades, application of remote sensing observations in Earth applications have increased a lot, and there are many satellites available. Currently, 4,800 satellites are orbiting or are in the space and basically monitoring or collect data from Earth. Majority of these satellites are telecommunication, basically satellites. So those are communication satellites. But pretty much about 25% of them are the ones that being used for Earth sciences. There are satellites that are relatively close to the Earth and they orbit around the Earth. So if we have the Earth, actually they orbit around it. And the advantage of these kind of satellites are that they are closer to the Earth, and they can have a relatively higher resolution of data, spatial resolution, but not as frequent probably as we would like to have. On the other hand, we have satellites that are way farther away from the Earth, and the feature, the characteristics of these satellites, which are called geostationary satellites, is that the location of the satellites with respect to Earth is always locked. So if Earth actually moves up, the satellite actually moves with it. So it always constantly looks at, one disk of the Earth. And with these kind of satellites, we have the advantage of going through very frequent observations, every few minutes, even depending on how fast we can transfer the data down to the Earth. And but the problem is that they are relatively coarser resolution in terms of spatial grid and pixel size. So if we look at the number of satellites in recent years, especially in the past few years, there's been a drastic, increase in the number of satellites, and probably more than 3,000 were added, 3,000 or 4,000 added just the last 3,000 added basically to what we had 3 or 4 years ago, and that's mainly because of a lot of private entities. They start to launch their own satellites. The satellites are getting actually more affordable to launch in terms of their size and the basically technology that we have. And the projections are that we're going to have another 2,000 satellites basically being launched in the next a couple of years. And that shows the huge amount of data that are being actually transferred to us and will be available to us for various applications. So here, if we talk about a little bit of how these satellites work, is that basically what they do, there is a platform, a carrier, the satellite, and then there are sensors on board these satellites. And depending on the type of a satellite that we have, they could be polar orbiting or geostationary. And these sensors collect data at various, frequencies and various wavelengths. So we know that the energy usually it transfers through the waves and electromagnetic, basically radiation that we call it. And the energy increases once the frequency increases. On the other hand, once the frequency increases, we know that the wavelength actually decreases. Our body or our eyes are sensitive to the visible light, so we know visible and regular images that are pretty much very narrow spectrum of these energies that we receive. So the advantage of actually these sensors of satellite is that they could actually put sensors on various frequencies and wavelengths and collect information from those specific bands. And each of these categories, from let's say ultraviolet, visible, infrared, microwave, these are the pretty range that these four basically categories are the ones that are mainly used in earth sciences. And looking at the features that we have on the earth, depending on what we see or the satellite see, the spectral response or the sensitivity of the sensors at different bands or wavelengths will be different for different materials or objects on the ground. So these are some examples how vegetation, dry soil, wet soil, or a clear lake versus a river will be responsive with respect to basically different wavelengths. And so these are unique characteristics of each spectral response will be helpful for us to detect what we are actually interested later on in our any environmental or earth studies. So the way that these sensors work is that we know that the source of actually energy mainly for in our planet is the sun. On the other hand, we know that any object above 0 degree Kelvin, which is negative 273 basically Celsius, anything above 0 degree Kelvin will emit energy at various actually frequencies. However, the intensity of the energy increases at these bands once the temperature increases. So sun is 6,000 Kelvin temperature. So that's why it has a very tremendous amount of energy basically being emitted by the sun. And we're talking about 80 million, up to 80 million watts per meter squared, actually, in terms of the radiation intensity. On the other hand, if we look at the Earth, the average, let's say temperature, let's say if it's 280, 300 Kelvin, that will basically create a very relatively small number of amount of radiation compared to the sun. And we're talking about between 0 to 16 versus 80 million in terms of the units of the radiation. That's why the majority of the sun's radiation is in the visible range. And as you can see, it peaks actually during that particular spectral range. And that's basically the whole light and basically the visible range basically helps us to have on the Earth. On the other hand, the Earth is majority of its basically radiation is from its temperature. And that's about the 11 micron basically here in this case that will help us to emit energy. So the satellites, the sensors are designed somehow that they can collect information either by what is being reflected after radiations from the sun reflected by the Earth, or the emission by the Earth as a black body, actually, which is in this case is it's kind of a gray body that we receive. So sensors at different bands and different, um, frequencies, they can actually collect information from Earth using the platforms that I mentioned. And when we talk about the remote sensing, there are different nature in terms of the signal that they're receiving, and they have or they are in various resolutions. And the resolutions, we normally know resolution as the spatial resolution or the pixel size, but there are more resolution types in satellite remote sensing. The first one is the spatial one, which all know about how big is the single pixel and the single data collected basically will cover on Earth. What is the footprint of that? That will be basically the spatial resolution. The spectral resolution, it's basically is at what band we're collecting the data. Are we at the visible range, red, green, blue, or are we in the range of near infrared, microwave, or basically lower frequencies? And the next type of resolution is about the temporal resolution, is that how often the data is being collected by the satellite, and satellites vary a lot in terms of their temporal resolution. And lastly is called radiometric actually resolution, which is if you think of the color green, you could have different shades of the green. So how sensitive your sensor is in terms of sensing these different shades. And so that's kind of a color depth, and that shows that how narrow that spectral response is at what particular range of spectral the data is being collected. This is a figure I like it really a lot, which basically summarizes all different types of resolutions in one graph for a few satellites. And as you can see at the bottom, we have the spatial resolution. The more we go to the left, the finer resolution will be. The temporal resolution in the y-axis, and then the lower that is, it's like the more frequent observations. And as we go higher, that resolution changes. That's in a logarithmic actually format. The other change basically is in the radiometric resolution. That shows that how narrow the spectral is. The narrower the spectral, the more intense the received radiation will be. And the last one is the nominal spectral, that at what bands we are using these satellites. So depending on the nature of our study and our work, these satellites at different various temporal, spatial, radiometric, and spectral resolutions will be applied. And these are some of the applications that need basically that kind of a resolution. For instance, if you're looking at the climate study, you are looking at, in terms of decades of response that we are focusing on. And the climate usually doesn't, we don't focus on the microclimate. We're talking about a global climate, and the very coarse resolution of kilometers will be sufficient for what we are actually trying to achieve. On the other hand, if you're looking for the emergency responses for a fire detection or location of fires or earthquake and those kind of applications, you may want to have a very fine resolution of data as well as a very frequent one, because those are very time sensitive, and they might be actually needed at the very fine temporal and spatial resolution. So what are the benefits of the remote sensing compared to what we have from our traditional or long-term data collection, ground-based data collections? The two major benefits of remote sensing are technically the spatial and temporal coverage, meaning that they can, without basically having any limitations, we could cover a very large area, relatively large area, using using the observations that we could have. On the other hand, the temporal coverage is something that will be very helpful for most of our applications. The other benefits of remote sensing could be that there will be no issue of accessibility to the region that we are interested. So if it's the place is inaccessible in the polar regions, in the mountainous region, in anywhere, basically these data could be collected, and in that regard are very more accessible. And the field work and the time that we will be spending, so obviously will significantly decrease with use of satellite information. In addition, the variety of scales and spectral resolution will give us the opportunity for modeling, for more modeling opportunities, meaning that we are talking about a very large spectrum of data, let's say from ultraviolet for the ozone, studies, up to, let's say, microwave range, which is for the precipitation and soil moisture, and anything in between will have a very high multi-spectral resolution that could help us to apply various modeling studies. Overall, remote sensing is more cost-effective. Thinking of the numerous actually ground observations that's in the global scale, if you think about it, the cost that all those in situ measurements will have in terms of a manpower as well as the equipment themselves. In the long run, remote sensing is more cost effective. And with the recent actually cloud computing, we will have more capabilities of handling the data, and those are something that will make the applications in a regional and global scale more feasible. However, there are limitations to remote sensing, and it's not like all the time that we can benefit without any issues from them. There is one misunderstanding about remote sensing, that remote sensing can provide directly about parameters or the measurements that we are looking for. However, what remote sensing does is collecting radiations from the Earth using the sensors that we are actually having them on board at the various spectral ranges. In other words, they do not directly provide any physical, chemical, biological information. And so that has to be considered. For instance, temperature is being a lot used using satellite remote sensing. However, sensors, they do not collect temperature directly, and more processing are needed in order to achieve to the parameter, let's say temperature, to the point that we could use them. So I put actually kind of a solutions or the ideas to overcome these limitations is that through the modeling and some radiative transfer models, basically we could achieve to the type of parameters that we are looking for. The other issue is that the signals received by the sensors usually is a combination of the surface and atmosphere. So the sensor is in the space, we have the surface and we have the atmosphere in between. So the sensor sees all of them together. So atmospheric effect removal is kind of inevitable actually here. The penetration depth issue, which is an issue that usually satellites have a very limited penetration depth. So they cannot provide a very deep information. Let's say if you're looking at the lake's stratifications, remote sensing cannot provide such information. So it's all we can do, the surface temperature, and then through some integration with other modelings, we may be able to overcome this issue. In general, requires is kind of a special training, not just in terms of applying them, but in terms of making them ready to the parameters that we're looking for. So a lot of radiative transfer, basically, knowledge required to make the data ready. However, in the very recent years, the availability of the higher level products, they're called higher level, means that they're already processed by scientists, and they are now ready to be used. So these days, probably, for instance, Landsat provided, has infrared bands, and those infrared bands, one had to always work and retrieve temperature out of these bands. But currently, we have those temperature observations calculated and provided by NASA. So this is something that these days we have less issues with these information. Satellite observations require calibration and validation. So that's where we need to do ground measurements and cross-calibrate them with other satellite observations. There are tens of satellites that they could be cross-calibrated. There's something that has to be considered is that there is no point measurement. The satellites is an aggregated representative of the scene and a pixel. And so we're looking at a pixel, it's the information that you get is a radiation from that area. It's not a point measurement. So if you have a heterogeneity or various basically land cover or features, that will cause that what you will be receiving will be actually an aggregate result. Satellites usually have the higher initial cost, until design and launching them, and computationally could be expensive in terms of the amount of memory, storage, processing, computer processing. However, with the cloud computing and the machine learning, that has been overcome. And in terms of the initial cost, as I mentioned, in the long term is a more affordable option compared to the ground observations. And lastly, there are always mismatch between the resolutions that the satellites provide in terms of spatial, temporal, spectral, with what we need, and the solutions for these, which has increased recently, is that the data fusion from multiple satellites, multiple temporal, spectral, and spatial, has helped to alleviate basically this issue. Applications have been very general, in particular for lakes that we are actually discussing here. They have been used for hydrology and climate studies. Surface temperature has been used a lot. Lake ice phenology has been studied with remote sensing observation. Water quality in general, HABs and cyanobacteria, sedum, total suspended matters, COD, and phosphorus and nitrogen are at least, the major parameters or phenomena that are studied using satellite remote sensing. This is an example of the satellites particularly for water quality in general. It could be marine water quality or inland water quality. And so with different spectral, spatial, and temporal they could be actually used. So the options are increasing day by day, as I mentioned, with the huge number of satellites that are being launched. So as myself, my involvement and being interested in lakes started, as I said, my focus has been actually remote sensing on different applications, but it started with the Lake Urmia in Iran, where I'm coming from, and that's basically the second largest salt lake and salt lake actually in the world, and it's the home of many habitats, and the lake started to have issues post 2010, and which losing a lot of water extent. So what we actually started to look at, the satellite observations to see that how they basically the water is changing. This particular lake, it's very close to another lake. It's called Lake Van in Turkey. It's about 100, 200 miles with a similar climate region. But as you could see that the lakes actually area decreased significantly in Lake Urmia, and Lake Van was relatively stable. And that kind of was an indicator that local mismanagement was an issue. So we published a paper back in 2014, and that particular paper received a lot of attention. And since basically it's about a decade that at least the local government is thinking about it. And to what extent they are actually effective, that's another story. But at least something that it received a lot of attention in the region and worldwide. So once we saw that basically that issue in Lake Urmia, we said, that what is going on in other lakes, and we noticed that Lake Urmia is not alone. There are tens of lakes worldwide that are shrinking, and we thought that is there any way to start looking at these lakes and try to relate them to, is there any way to discern that if it's a climate issue or if it's a local management issue at a global scale, to see that how lakes are changing. So these are some examples of the lakes that are basically kind of dying, and that motivated us, that what if we actually do the variations in temperature for around these lakes, and looking at the temperature changes. So the idea here was that this is Lake Urmia at the bottom right, is that showing in the region over land, there was no change in the temperature, change. And so temperature was relatively stable in the region. However, over the lake, the temperature was increasing. So that means that, they were slowly drying out and basically creating higher temperature. So that indicated that it could not be climate change, because you should see some signals in the surrounding land's temperature as well. So that's something that we did not see in Urmia. So maybe it's something that the mismanagement could be actually blamed in this case. However, there are places like Bolivia, which Lake Pupu actually is. We saw that the increase in the temperature is happening in the whole region. So it seems that the climate change effect is more of an issue in this particular lake. So we thought that why don't we actually do this for many, many lakes worldwide? So let's look at the lake's temperature. Let's look at the water temperature in the lake. the surrounding land as well as the water, and see that if there is consistency, if they are both going up, if they are both actually pretty neutral, or one going up, one basically not changing. So these kind of discrepancies actually might be helpful to have a better understanding about these lakes. So this is the work with by my graduate student. So he's still trying to make the final publications and other publications out of this, that he started actually looking at these lakes, and he studied more than 500 lakes globally. The numbers are increasing, so he's going by the sizes, from the largest lakes to the smallest one, and they are looking at the temperature variations in the past 20 years using MODIS observations, and what he's looking at, land temperature as well as the water temperature and the differences between land and water temperature. So this is an example again in Lake Urmia that's showing that we know that land is relatively warmer than water bodies, but in this case we see that because water temperature is rising, the differences between the two is decreasing. So we thought that if we can find the slope of these temperature variations for each lake, we can actually map them out. And these are some results from those lakes that show that some lakes are cooling, some lakes are warming, and basically we looked at both water and land. This is the map for the water. He did some hotspot analysis of them to just categorize what regions doing, how they are doing, and for instance, we see it in the southern, U.S. They're actually warming in the higher rates, as well as the places that, let's say, in China or Russia, we have cooling effects of the lakes with respect to both water and land. In a parallel study, we did, the surface area variation, and we are looking actually linking these lakes, that how they are changing, these temperature land changes, how they are related, if they are shrinking or growing. And what we found is that those that are shrinking in general, the differences between the two LSTs basically was and basically changing, that the slopes are actually different. The slopes of variation in land and water is more different than those that are relatively growing. In the next remote sensing related, we focused on the harmful algal bloom and chlorophyll A concentrations. This is a study back in 2018 by an RE student at the Carey Institute. What he did in the states of Maine and New Hampshire, he looked at, I believe 78 lakes, and he used various models that exist to detect chlorophyll A. There are many global models are available. So what he did was he looked at these models, and he concluded that the results could vary a lot if depending on the region that we are looking at, and the extent that basically looking at. If you're getting a good results at the global scale, it doesn't guarantee the regional basically applicability of the particular model. And we found some contradicting actually results. So that showed that these models using Landsat, for instance, in this particular case, has to be tuned and calibrated for a particular region. This is a work with my colleague Marzi, that in our group, that she started actually looking into the chlorophyll A and HABs and looking at the extent. So usually there are single observations from point observations from for chlorophyll A or multiple water quality parameters. So what we have here is that the data are generated for the whole lake, and this is the advantage of using satellite, that you can define the extent of the variability. And they actually, in this particular case, are well in agreement with what those ground observations. In addition, this is a lake in Lake Hopatcong in New Jersey. This is the largest lake in the state for various recreation and other purposes. And in the past, in 2019, there were actually flyovers, basically observations of the lakes, and several flights actually happened at different months. And we started looking at, how they are in agreement when we actually looking at these flights, and showing with the, let's say, green and red, yellow, they actually are in agreement with what we have. In July 2019, it was a huge issue with harmful algal blooms, in the lake. They had to close the lake. It's a huge lake with a lot of people living by a lot of recreation activities, but they had to close the lake to the public because of this advisory issue in the lake, that the results actually from satellites actually confirm the same issue. The situation got a little bit better later on in August, and back to normal in September. So that showed that it's the observations that the modeling that Marzi did with Sentinel-2 observations are very good, in agreement with what those ground-based and airborne-based airborne observations that we had. The other main advantage that I mentioned, the spectral variation that we have using the remote sensing observations. So if you look at the spectral variability of observations that we have from Sentinel, let's say, or Landsat or other satellites, they can actually provide an insight how they vary actually at various bands. And this is what she found, that that relative to the orange one, the advisory, the blue one, let's say at the watch level, and the green is the clean one, they are pretty actually showing some signals that could be used actually to use multiple bands at the same time. That's where machine learning or other basically approaches could be helpful to generate more accurate results. This is another one that shows that the bands, advisory one versus the ones that are in the watch or clean scenarios. Another lakes related study that we did using remote sensing was using MODIS observations actually for GPP, gross primary productions. I'm not a limnologist, but we help basically. We did the remote sensing aspect of the work. This is another student that we had at the Carrying Institute, and this is on the publication that showed the very relatively good agreements between what we can get from MODIS observations versus inland model GPP or observations that we have. So that was another useful. The issue is that these are good for only the lakes that are in the order of kilometers, and if they are actually small lakes or ponds, we might not be able to use MODIS observations. In another study by Abdu and Sophia, another student, the lakes ice phenology was used using MODIS observation. they created a model that would detect basically ice cover, the ice in and ice out, timing at the lakes. Lakes in Maine were targeted in this particular study, and relatively promising results were found that when we look at the both ice in, when this ice started and when the ice is out, from MODIS observations versus the observed ground observed data. They looked at, that how lakes geomorphological, effect, characteristics may affect the accuracy of the results. For instance, they found that in lower elevations, they have more issues, or for smaller lakes, they have more errors versus the ones that are having bigger perimeter or surface area. The results again showed year by year pretty good agreement with what they have found for various lakes. The data range of the ice in and out for both colors are mentioned here. And the next project that again Abdul is heavily involved is the water temperature validation, and that's the work that it's been started since last year within GLEON, and I'm going to ask basically that if you're interested to join this work, please contact Abdul. We would like to hear from you to use your expertise as well as your data or ground observations if you have. Well, the goal here is to do global validation of the surface temperature using satellites. And the reason is that when, let's say, NASA publishes the temperature products for MODIS, they do not specifically validate them for the lakes, because lakes are a very, very small percentage of the land cover. So if they're actually providing the land temperature, majority of the validation efforts are focused on over land at various land covers. But the study of lakes and the validation is kind of under studies. We think that this is kind of necessary, and this is what they're actually focusing on. And the last one that I'm going to actually focus on is kind of an opportunity I see as a potential for future expansion of applications of remote sensing, is to use active microwave. In this particular case, this is an image from Sentinel-1 that could be used for a very small ponds, lakes. The advantage of the very high spatial resolution, as well as not being affected by cloud and atmosphere in SAR observations, synthetic aperture radar observations, are very advantageous for the applications that we are interested in. However, the problem is that they are very intense in terms of the size. A small tile of these regions could actually be in the order of gigabytes. And so if you're going for let's say 100 kilometers, you might need to download terabytes of data to look at a few years of observations. They require a lot of processing, step-by-step processing at different levels. And that makes them a little bit, more challenging if you don't have the expertise actually to go through this. It takes time to be trained to be able actually to perform such analysis. However, I think that the return of the results worth it, and I think it's worth trying. And I'm sure that we will be hearing more the application of active remote sensing versus passive one, which in the active scenario, the sensor sends actively a signal to the object, and it collects the scattered observations from the objects, and depending on the intensity of the return signal, they can actually provide information about different characteristics of the object. So with that, I would like to thank my my team actually at the Center for Remote Sensing of Earth System Sciences, for many past and present postdocs, graduate students, and undergrad students, and other faculty members in our center. And I also would like to acknowledge the funding agencies that funded our projects. So I think that I would like to stop here. Thank you.